Welcome to lesson 7.4, applying properties of similar triangles. The learning targets for this lesson is that you will be able to use properties of similar triangles to find segment lengths and to be able to apply the proportionality theorems. There's actually more than one because of the converse. We're going to start by looking at 7.4.1, and you can copy down what you see of this theorem. If a parallel line to a side of a triangle intersects the other two sides, then it divides those sides proportionally. So here's an image, and we have that same image right here in our notes. So the conclusion for this, because of the parallel lines, is that the ratios of the sides that were split into pieces, those pieces AE over B or EB, will be equal to AF over FC. Now normally, when we were solving in lesson 7.3, we had to be very particular that we were doing a side length of a triangle, AE, over the full side, AB. But because of this proportionality theorem that you're seeing right here, as long as we are given that this line that's cutting it is parallel to the base of the triangle, then I actually don't have to take the full side length. I can actually do piece over piece equals piece over piece. All right. So using this theorem, we're asked to find the length of a line segment. In this case, we're asked to find the length of US. Well, US, we're going to call X. Now, in 7.3, we would have said RU, 14 over RS, 14 plus X. But because of these parallel lines, we can use the triangle proportionality theorem to say that RU's piece over the bottom piece of RS was split into two pieces, this piece and this piece. The piece that's closer to R over the piece that's closer to S is going to equal the piece that's closer to R on this side over the piece that's closer to T on this side. So we have 14 over X equals 10 over 4. And so when we cross multiply, we get 10x equals 14 times 4, which is 56. So 10x equals 56, which means x is 5.6. Now that's the value of x. They were asked to find US, which we labeled x. So US is 5.6. 1b. Again, we have the parallel lines. If we didn't have this, the only time you can do piece over piece equal to piece over piece is if the lines were given as parallel. So line NM has been cut by a parallel line to the base. So this piece over this piece, x plus 1 over 2, is going to be equal to this piece, again closer to n, over this piece. If you start with the one closer to n on this ratio, then you have to start with the one closer to n on this side over here, this ratio, 10 over x. If you had x over 10, you would get the incorrect answer. When I cross multiply, I get x squared plus x equals 20. So I'm going to subtract 20. I have x squared plus x minus 20 equals 0. The factors of 20 are x plus 5 by x minus 4, multiplying to negative 20 and adding to 1 in the middle. So x equals negative 5, or x equals positive 4. Well, if I put in negative 5 for this side length, or even that, it's not a true side length, so that's extraneous. Our answer for this is x equals 4. We were asked, however, to find Qn. Qn would be 4 plus 1, so Qn is 5. Next, we'll look at the converse of the triangle proportionality theorem. The converse of the triangle proportionality theorem, well, the original theorem said if the line that intersects the triangle or cuts through the triangle is parallel to the base, then the proportions are equal. This one says if the proportions of piece over piece, if it's proportional, if it's equal, then these lines have to be parallel. If the pieces are proportional, again, the pieces we're referencing as written right here, from A to E, E to B. If a line divides two sides of a triangle proportionally, then it is parallel to the third side. So if the pieces are proportional, then the lines are parallel. Then the line is parallel to the base. So we're going to conclude that EF and BC are parallel. So this is an exception, while it still is a converse, huh? Notice the other lines that proved lines parallel were converse of cap, converse of alternate interior angles, converse of alternate exterior angles, converse of same side interior angles. Now we're saying that if these ratios are proportional, then by the converse of triangle proportionality theorem, the lines are parallel. So we're supposed to verify for these problems that the lines are in fact parallel. Well, so we need to see, first off, is it proportional? So we're comparing AD to DB and AE to EC. 10 over 15 does, and we're testing, is that equal to 8 over 12? Well, you can either reduce these as fractions or cross multiply. Here I get 120 when I cross multiply. Here I get 15 by 8 to be 120 as well. So they are proportional. So we can say DE is parallel to BC since AE over EC equals AD over DB. Triangle converse of triangle proportionality theorem. Converse of triangle proportionality theorem. Letter B. They tell us AC, the whole thing is 36. Well, if the whole thing is 36 and this piece is 20, then this piece is 16. BC, the whole thing is 26. 26 minus 15 is 11. So I'm going to check real quick to see if these are parallel. 20 over 16, is that equivalent to 15 over 11? Notice I always start with the one closest to the top of the triangular point, the vertex on the triangle. So 20 over 16, 20 times 11, I was actually going to reduce, but whatever. 220 equals 16 times 15, which is 240. They are not equal. So no, the CD over DA is not equal to CE over EB. They're not proportional. So our answer is no. The lines are not parallel. DE is not, there's me crossing out the parallel symbol, parallel to AB. And our last theorem for these notes is the two transversal proportionality corollary. A corollary is a mini theorem that is derived from a major theorem like the triangle proportionality theorem or its converse. In fact, we're looking at the converse derived from the proportionality theorem. And this says if three or more lines intersect two transversals, or I'm going to say cut two transversals, then, and they have to be parallel. Three or more parallel lines, they have to be parallel. Cut two transversals, then they divide the transversals proportionally. I'm going to write then transversals are cut proportionally. What does that mean? That means, here's an example, that we have these parallel lines. These three lines are actually parallel to each other. This means that AC over CE will be equal to BD over DF. AC over CE equals BD over DF. Now, if these other transversals are actually parallel, then not only will they be proportional, but they'll actually be congruent. But if they're not parallel, the reason this is a corollary is if I extend the lines up that would form our triangle, then again we have pieces of a triangle, and so this is partly how it's derived from the triangle proportionality theorem. So we're going to look at an example. It's a little tough to see the example. I'll try to zoom in. They do give us the numbers, at least in the wording of the problem itself. So it tells us that KL is 4.9. These are all in inches, so that's helpful. BC, that I can read that one. KL, they didn't give us any other ones. That's it, 4.9. So right now, if I'm trying to find LM, I have to solve for one thing at a time. Unless I have a system of equations, I can only solve for one thing at a time. I want to find LM. LM matches up in the picture to BC, okay? But if I'm looking at piece over piece, I'd have LM over 4.9 equals BC over AB, so 2.6 over 4.5. And I can call LM X if I want. So piece over piece on this transversal, piece over piece on this transversal. So now when I cross multiply, 4.5x equals whatever 4.9 times 2.6 is, which is 12.74. Divide by 4.5, x is 2.83, or approximately 2.83. We could get a fractional value. It's going to be very large. But since we're rounding anyhow to the nearest tenth of an inch, we could just say x is 2.8 inches long. So that is, x is what we defined as the distance from L to M. So the distance from L to M is 2.8 inches. Now they also ask for MN. Again, pieces are proportional, so I can do MN to CD, and I can even compare that to, again, LK and AB. I don't have to use the middle. I could do this to the whole thing and this to the whole thing, but I'm not necessarily going to have to do that. So I have MN over 4.9 equals 4.1 over 4.5. As long as these lines are parallel, and we're assuming, okay, in the sketch, that the trees are parallel. The trees are parallel. They're all perpendicular to the ground. Trees usually grow perpendicular to the ground, and so that's why we're assuming the trees are parallel. If they weren't, then this wouldn't work. So now we've got 4.9 times 4.1 divided by 4.5. So 4.5 equal M times MN equals 20.09 divided by 4.5. MN is roughly 4.46. 4 repeated. So the nearest tenth, we'd say MN is 4.5 inches. And that concludes the video notes. Feel free to give problems 1, 2, and 3 a try. We'll be discussing these problems in class tomorrow in your groups. Have a good day.